In the last step of the previous lab, we tried training our CFAR10 model on a single machine. Training on a single machine can be time-consuming. However, scaling to use clusters can be expensive and require a lot of work to provision and manage the machines in the cluster. Google's ML engine provides managed infrastructure that allows you to scale your training and deploy your models to the cloud.
Let's compare the amount of work it would take for you to train and deploy a model on ML Engine versus training a model on your own distributed system. With ML Engine, you won't have to manually provision the instances in your cluster and set up their environments. Instead, you can specify the amount of computing power you need in your configuration, and ML Engine will provision your instances automatically. When it comes to deployment time, you also won't need to set up any complex infrastructure. ML Engine will handle scaling your model. You just need to have a TensorFlow saved model in a cloud storage bucket. Personally, I don't enjoy the work that comes with needing to maintain a cluster, but I understand that everyone has their preferences.
In addition to being a managed service, ML Engine integrates nicely with a number of other Google Cloud products, including Cloud Storage, BigQuery, and Dataflow. As mentioned earlier, you can deploy your TensorFlow models to ML Engine and use it to run your models to get predictions. To deploy your models to ML Engine, you must export a model to a TensorFlow saved model and upload that saved model to a cloud storage bucket. Please note that you cannot use a checkpoint. You can use a model that you trained locally once you upload it to a cloud storage bucket. Being a managed service, ML Engine scales serving nodes in response to traffic. It does this by trying to reduce latency for online predictions and job time for batch predictions.
Now that we are familiar with the CFAR10 dataset and the capabilities of ML Engine, let's dive deeper into the processes involved in building ML Engine models. First, we'll look at training. We can split the training process into 4 steps: preparing the trainer app, packaging it, submitting it to the ML Engine, and then monitoring the training job. Let's look at the first step. If you're developing a trainer with the recent TF conventions, you should be able to use it in ML Engine with minimal modifications. Here are some of the main considerations you need to note when developing your trainer. Parameters are passed to ML Engine as command line arguments. You'll be using these parameters when submitting your training job and for hyperparameter tuning. To help with this, TF has the TensorFlow.app.flags module that lets us define parameters as command line arguments with a minimal API. In this example, we define several flags used in our trainer. Flags.job_dir will be set to the command line argument we pass when running the task. ML Engine makes it easy to run training jobs distributedly. It uses the environment variable tfconfig to pass cluster specification and task information as JSON string. We'll briefly discuss more about distributed TF later when we get to submitting training jobs. Next thing to consider is storage. ML Engine automatically provisions instances to run our training jobs fully managed and at scale. These instances have ephemeral storage since they were meant to be short-lived. That means we need to persist data somewhere else. TensorFlow has deep integration with the Google Cloud Platform, which allows us to transparently use cloud storage paths throughout TF's API. You should take note of the region of your cloud storage buckets. Make sure you have them in the same region as your ML Engine job to avoid any unnecessary latencies. After training, you'd want to export your trained model in saved model format. The number one reason to do this is that ML Engine only accepts this format in its prediction service. But there are several other benefits of doing so, such as support for multiple graphs, signatures, external assets, and clearing devices. Step 2 is packaging your trainer app. ML Engine only needs your app installable as a standard Python package. This mostly means creating a setup.py file and organizing your trainer app files into modules. Here's a sample project structure you can use. Note that you don't need to write setup.py or build your package manually if you're using the gcloud command line tool. To build your package manually, run python setup.py sdist for the source distribution and python setup.py bdist_wheel --universal for a binary wheel. After packaging the trainer, we can now submit it to ML Engine and run a training job. Since training can take from a few minutes to several days to run, ML Engine executes trainer apps as jobs we can monitor. To submit a training job, you need to supply several parameters and send a request either directly through the REST API or the more convenient gcloud tool. We will be using the gcloud tool for our examples. First is the job name, which is used as the unique ID for the job. It's common practice to suffix the job name with a timestamp. We supply trainer package either as a path to the unbuilt package directory through the package path argument, or a path to the built packages through the packages argument. These paths can either be local or from Google Cloud Storage. We also pass the name of the entry point module that ML Engine will be executing. Job dir is an optional convention. ML Engine doesn't really use it directly. Your trainer app needs to know how to read and use this argument. Region determines the data center location your worker will be coming from. Runtime version defines the environment your job will be running in. Last is the cluster configuration. You can use predefined configurations with scale tiers or define your own custom cluster. These are the available scale tiers in ML Engine. Basic is good for trial runs with small datasets. Standard provides more workers and some parameter servers. You can use premium for models that require a beefier setup, while the basic GPU tier allows for more efficient training of models that involve a lot of mathematical operations. Use custom to define your own cluster configuration. Note that selecting a predefined scale tier won't automatically make your trainer run distributedly. You still need to configure TensorFlow for this to work. TensorFlow makes it easy to run training jobs distributedly. You just need to specify the roles and addresses of the nodes in your cluster and start a server on each node. TensorFlow will know how to make the nodes communicate with each other and execute parts of the training job in parallel. ML Engine uses the following task types or job names: master, worker, and PS for parameter server. There's a sole master node in any cluster. It handles orchestration and gives the overall status of the training job. Export and reporting is usually delegated to this node. Worker nodes share the workload for training, while parameter servers hold shared parameters used to coordinate the workers. Custom cluster configuration is written in YAML. We can set the machine types for each task type and the counts for workers and parameter servers. ML Engine will spawn instances specified in the cluster configuration and provide an environment variable named tfconfig, which contains a JSON blob describing the roles and addresses of the cluster formed. Putting it all together, here's a sample job submission. Notice how the date program is used to add timestamps to the job name. We are using the custom scale tier, passing cluster specification through the config file, which we'll see on the next slide. A couple of extra training arguments are also passed at the end of the command. Training jobs take a while to finish, so it's ideal to have visibility on their status while running, and their logs in case they fail. You will see this message after submitting a job through the gcloud tool. The first command prints out the current status of the submitted job, while the other command streams out logs. Above shows what the streamed logs look like. You can also view the logs from the web console through Stackdriver, which is Google's monitoring and logging platform. ML Engine also provides basic resource utilization charts that help monitor usage. It's also very easy to run TensorBoard for your training job. Since we use cloud storage for our training job artifacts, we can just point TensorBoard to the logs directory and it will just work. After going through all the steps, all you need to do now is wait for the training job to finish. Or train again because it failed. This is where the timestamp suffix becomes useful. You can run the same job submission command over and over again instead of manually editing the job name each time you try to submit. Job failure will be a common occurrence, especially at first while you're still getting familiar with using TensorFlow and MLEngine. To help ease the burden of troubleshooting and debugging your code, here are a few tips. Log everything. Since we're dealing with ephemeral instances, the only places you can review when something goes wrong is the cloud storage bucket you used for your training artifacts and the logging you set up in your training app. Be generous about logging and make sure to add proper tagging to make it easy to filter stuff in Stackdriver. Also, it will save you a lot of time and credits if you make sure that things work in your development environment first before pushing to MLEngine. The gcloud tool has the gcloud MLEngine local command to help test your trainer code locally. Lastly, make sure to check the examples provided by Google and other sources. You can pick up conventions and tricks that you will otherwise miss by just reading documentation. And after a bit of hair pulling and keyboard smashing, you will eventually encounter the glorious green checkmark signifying a successful training job. But wait, there's more. MLEngine has support for a couple of features that help create better models and train faster. First is Hyperparameter Tuning. Hyperparameters are parameters that are set prior to the training process, such as the learning rate and batch size. Proper setting of hyperparameters lead to better and sometimes faster trained models. MLEngine can automate the tuning of these parameters by running training trials multiple times and adjusting the values taking into account trial results. There are a few things to note when you're using hyperparameter tuning. First, you need to properly log summaries to event files for MLEngine to adjust hyperparameters correctly. Next, hyperparameter values are passed in as command line arguments. You can use 4 value types for your hyperparameters. You have double, integer, categorical, and discrete. The type of scaling used for adjusting numeric values can be linear, log, or reverse log. It is recommended to set the max number of trial runs no less than 10 times the number of hyperparameters used. And finally, parallel trials are faster, but doesn't take advantage of MLEngine's tuning. Hyperparameter config is specified in the same YAML file defining your cluster configuration. You first set the criteria for a successful trial. In this example, the goal is to maximize the recall at 10 metric tag logged in the events file. Max number of trials is set to 10 with 5 parallel trials. The parameter to be tuned is learning rate, starting with a value of 0.001 to 0.03 scaled logarithmically. One last tip for hypertuning. Use a different training output path per trial so you can review the complete results of each trial later on. And last but definitely not the least, MLEngine also supports training with GPUs. GPUs can boost training speeds for certain model types. Using GPUs for training in MLEngine is as easy as switching to machine types with GPU support or by using the basic GPU scale tier. Note that GPUs are only supported in US East 1, US Central 1, Asia East 1, and Europe West 1 at the moment. They are also not enabled by default. You need to submit a code change request to have them enabled for your projects. Now let's put all those theories into practice. Pull the lab notebooks from our GitHub repo and follow the instructions. By the end of this lab, you should have your own trained CFAR10 model and a web app that can classify images and turn them into emojis.